Hi everybody. So I'm making this video to talk a little bit about the Module 11 activity. As I've been grading it, it's really become apparent to me that there was a lot of unclarity about exactly what to do or how to be successful in this activity. And for me, I feel like when something like that happens, clearly a message didn't get across, and so I feel like I really owe it to you to go over this activity. And then what I'm going to do is right after I'm done with this, I'm going to create a new activity that you could submit to get a better grade. Okay? So let's do this. The first question on this activity, pretty much everybody got. All I'm asking here is just for a definition of each of the 4 non-modeled forecasting techniques that were covered in this week's lectures, which were persistence, trend, analog, and climatological. Now, with that said, I think that a lot of what went wrong in the next few problems had a lot to do with a misunderstanding of how to apply these techniques. So if you feel confused or if you feel unsure, let's do it and we'll get you covered, okay? So let's go ahead and talk about this. So, actually, am I recording? Oops, yes I am. So, let's go ahead and do this. So, for problem 2 here, I actually gave you a set of data on the next page. And here's what this data was actually showing you. So, I gave you weather conditions for yesterday, which included the high temperature, the wind speed, and the cloud cover, as well as precipitation. And then I also gave you today's weather conditions, which included high temperature, wind speed, cloud cover, and precipitation. Now, these are numbers that I got a few quarters ago, so they don't actually represent today's weather conditions, but you get the idea here. So this was yesterday's weather, today's weather, and then down here, this is the climatological average. So if you've ever watched a weather forecast before and they say something like, so the normal today is 67 degrees, what they're actually talking about is what's called a climatological average. Basically, for that date, this is the average of the last 30 years of weather data. And so that's what this 67 represents. That's the average temperature. Usually they don't get data for wind speed and cloud cover, so there's usually no averages there. And then this is the average precipitation for the day. This gives us an idea of what the weather, in a sense, would normally be like on this day. So now, how do we actually use these numbers in this question here? So what I was asking you to do here is make a forecast for tomorrow. So you're going to take the weather data that I just showed you and you're going to make a forecast for tomorrow. So for the first forecasting technique, you would use what's called persistence. And the idea behind persistence is whatever the weather conditions are today, they stay the same. So if you go back to the data table here, the weather conditions today were a temperature of 66, a wind speed of 20, a cloud cover of 20%, and no precipitation. So for a persistence, you would just do the same thing. So whatever the weather was today is the weather tomorrow. So we would get something like that. Today's temperature was 66. A persistence forecast would dictate that tomorrow's temperature is 66. And then you do the same thing for wind speed. The wind speed was 20. Cloud cover was 20%. And there was no rain, so using a persistence forecast, there'd be no rain for tomorrow. So that's a persistence forecast. Whatever the weather conditions were today, they stay the same tomorrow. Nothing changes. Now, what about a trend forecast? Well, a trend forecast requires at least 2 days of weather data. And I have 2 days of weather data here. I have weather conditions for yesterday and weather conditions for today. And the idea for a trend forecast is whatever the change happened between yesterday and today, that same change will happen between today and tomorrow. So for example, if it was 70 degrees yesterday and 66 degrees today, that means that there was a decrease in 4 degrees. That's a trend. So if we were to use a trend forecast for tomorrow, all we would simply do is subtract another 4 degrees. So if it was 70 yesterday, it cooled 4 degrees today, it's going to cool another 4 degrees tomorrow. And so using that, we would end up with a temperature of 62 Fahrenheit. A wind speed, well, we saw an increase in the wind speed from 17 to 20, so we'd see another 3 mile per hour increase to 23. For cloud cover, we saw a decrease of 10%. We went from 30% down to 20, so we'd go down another 10%, now down to 10%. There was no precipitation in either day, so there was no trend, no change in that. So you would just say, okay, since there was no difference from yesterday to today, there'll be no difference from today to tomorrow. Essentially, when there is no trend, you go back to persistence. Now, the one that I think most people got caught up on here was climatological. When I say climatological, I mean using the climatological average. No, that is not the average between persistence and trend. And no, it's not the average between yesterday and today. Instead, you're using this down here, these climatological numbers that I gave. Again, these tell us what normally would happen on this day. And basically, whatever this is predicting, you would just plop that up here. So if it was predicting a high of 67, or if the average high is 67, then using a climatological forecast, you would say, okay, so if the normal is 67, that's going to be our forecast. Since we have no wind speed and no cloud cover data, we can't forecast those. Unfortunately, those wouldn't work. We'd probably want to rely on other methods to forecast those. But for here, you don't need to worry about them. And then the climatological average also gives us 5/100ths of an inch of precipitation. So 0.05. And since that's the average precip for the day, you would put that up here. So the average precip would be 0.05 inches. Okay? And that's how you do the persistence, the trend, and the climatological. For the persistence, basically today's weather becomes tomorrow's weather. Oops. Don't mind the typos or the bloopers. As far as trend is concerned, the difference between yesterday and today becomes the difference between today and tomorrow. So we had a 4-degree change from yesterday to today. So we'll have another 4-degree change for tomorrow. And then the same thing goes for wind speed, cloud cover, and precipitation. Whatever the change was between yesterday and today, that would be the change between today and tomorrow. And then climatological just used tomorrow's climatological averages. All right? So that's how you would do the second problem. So take a deep breath, and then let's jump into the third problem. Now the third problem actually, and this is the one that most people tripped up on, and it might actually seem like the trickiest, but it actually isn't that bad. So Once I get you through it, a light bulb will go off. If it hasn't, please send me an email and we'll get that light bulb off. No problem there. But let's talk about it. So here I have 3 different cities, and they're each 100 miles apart. And I label them City A, City B, and City C. And at each station, or at each city, I also give you a station model showing the conditions. If you don't remember what a station model is, information on station models was all the way back in Module 1. But I can just give you a quick crash course here. This number in the upper left hand, this is the air temperature. The number in the lower left hand, that's the dew point. The number in the upper right hand, that's the last 3 digits of air pressure. In order to convert that, you would have to go through a process where if it's less than 500, stick a 10 in front of it. More than 500, stick a 9 in front of it. Again, that's detailed more out in Module 1. We've done these a few times this quarter. And then the shading on the inside, that's cloud cover. And then this stick that's sticking out of the circle, that's called the wind barb. And that tells you wind direction, and then the little feather at the end tells you wind speed. Okay? Now here's the tricky thing here. The tricky thing here is that rather than looking at how the weather changes at one location, from today, tomorrow, and so on, instead we're going to identify how the weather changes at 3 different locations. Well, it's tricky, but it's actually not that bad. So let's talk about it. So immediately I say, assume that weather systems move to the east at 100 miles per day. What I'm basically saying here is whatever the weather is in, say, City B, that weather is going to travel east at 100 miles per day. So whatever the city or whatever the weather is at City B, that weather is going to travel east at 100 miles per day. Well, luckily, City C is 100 miles to the east. So whatever City B's weather is today, it's going to be City C's weather tomorrow. So basically, the weather is moving. And this is actually very common. Weather conditions typically don't stay in one location. Rather, they move from place to place. This is what's called advection. Basically, it's the movement of air and all the properties in the air from one location to another. So basically, in a layman's sense, weather is moving. And it's moving to the east at 100 miles a day. So whatever the location is, or whatever the weather is at, say, City A, that's going to be City B's weather tomorrow. And whatever City B's weather is today, that's going to be City C's weather tomorrow. And this is a pretty crude approximation, but for the purpose of this class, it's good enough. Now, what kind of a technique is this? Well, we're not using any climatological averages here. So climatological is out. And weather conditions aren't staying the same. Why? Because everything's moving. So persistence is out too. Really, the only valid forecasting technique would be trend forecasting. And the reason why is because stuff is moving. Any weather and any weather systems are moving to the east. And so we can use that knowledge to make our forecast. That is an example of a trend forecast. So here's how we would do it. So whatever City C's weather is, those conditions are going to keep moving east. So they're gone. In order to replace City C's weather conditions, whatever's 100 miles to the west is going to be moving in. So basically, all that's happening here is that City B's weather is now City C's weather. So for tomorrow, City C's weather is city B's weather today. So here's what that means. All the weather conditions at city B are going to move over to city C. They move 100 miles a day. City C is 100 miles to the east. So everything at city B has moved to city C. So here's how this would look like. So for city C, temperature would be 67. Dew point would be 66. Cloud cover would be 100%, and so on. Basically, whatever the weather was at city B today is going to move 100 miles to the east. So it's now at city C. And then the same thing is true between city A and B. Whatever city A's weather is today, that's going to move 100 miles to the east and be over at city B. So for city B, it's also a trend forecast because stuff is still moving. And the temperature at city B would be whatever today's temperature was at city A. So temperature would be 58. Dew point would be 37. Cloud cover would be 0. And so on. So really all you're doing here is you're taking whatever weather conditions were at city B and you're moving them over to city C. And then you're taking whatever conditions were at city A and you're moving them over to city B. And this is because all of the weather and all the weather systems are moving east at 100 miles a day. Now the last question that I want to ask is, what kind of weather systems may actually be present here? Well, specifically, are there any frontal boundaries? If you remember, a frontal boundary is between one air mass and another air mass. And this is basically review. All I want you to do is look at the conditions between each of the cities and identify if there's a front between them. Now, in order to do this, you need to remember what the conditions would be before and after a front passes. In the case of a warm front, winds are usually blowing from the east and temperatures are usually really low. In these three cities, there's no location where the winds are blowing from the east. So I would actually completely rule out a warm front. There's no warm front here. Winds usually shift from the east to the southwest. And there's no situation where going from one city to another, winds shift that way. So warm front is out. But what about a cold front? In the case of a cold front, two big changes happen. First, you go from a warm temperature to a cold temperature. And second, winds usually shift from the southwest to the northwest. Now between city B and city C over here, winds shift from the south to the southwest. In this case, there's really no front between the two. Why? Because the winds aren't shifting in a strong enough pattern. Instead, if we look between city B and city A, traveling between B and A, winds shift from the southwest to the northwest. That's very common once a cold front passes. Very common once a cold front passes. The other thing you notice is that temperature drops pretty noticeably. Dew point drops pretty noticeably. That's very common for when a cold front passes. And weather conditions overall, as far as precipitation, cloud cover, they improve pretty substantially between city B and city A. So there's definitely something going on between these two cities. And looking at the conditions before the front, those would be the conditions ahead of the front, to the east of the front. City B is just textbook prefrontal conditions. Rain, cloud cover, winds coming from the southwest, while City A is textbook for behind a front. In this case, cooler temperatures, winds coming from the northwest, no clouds, and so on. So there is definitely some kind of front between these two locations. And I'm going to draw it pretty crudely here, but it gets the job done. Let's color it with blue for the color of a cold front. That's actually more like a purple. There we go. And I'm not going to put the spikes on it right now. Just note that's a cold front. So there's a cold front between City B and City A. City B is ahead of the front, therefore it has warm temperatures, southwest wind. City A is behind the front. Cooler temperatures, winds from the northwest. But again, this whole example simply is based on this right here. Weather systems move to the east at 100 miles a day. So persistence isn't going to work because things are moving. And since we have a known speed, that speed is our trend. So whatever the weather was at City B is going to move 100 miles between today and tomorrow, and that's going to be City C's weather. And then City A's weather is going to move 100 miles, that's City B's weather. I hope that this helped out, and I really hope that this at least sheds a little bit of light on this activity. It takes a little time, but definitely go back and review persistence, trend, and climatological forecasting, and hopefully that'll help make this a little bit clearer. I'm going to be posting this on YouTube immediately, and as soon as I'm done with that, I'm going to put up a new exercise. You'll have until Friday to do it if you want to do it. And then my plan is I will get it graded and back out by the end, or no later than Sunday night, so that you'll have it in your grade book and good to go. All right? And if you have any questions between now and then, please don't hesitate to reach out to me. All right? Thank you for watching this, and good luck on your finals this week.